Alright, let's get started. Here's where we left off. The next slides are some data graphs that I want you to understand. And to do that, I want to talk about a couple of concepts. When I talk about reabsorption and secretion. So you're transporting something per unit time. And what I want you to know is the processes of secretion and reabsorption have limitations. They have transport maximums. Because these processes depend on a finite number of pumps and carriers in the cell membranes. And when they reach their transport capacity, you have reached saturation or transport maximum for that substance. So, processes of secretion reabsorption. Have maximum limits. So when you reach that maximum limit, that's called saturation. The maximum rate of transport that occurs when all the available carriers are occupied. That's the term, saturation. When all carriers are maxed out. It's called saturation or transport maximum. T subscript M is the shorthand for that. So that means in the blood plasma which is being filtered, there must be a lot of that substance in the bloodstream if it's getting all filtered by the kidney. So then the renal threshold is the plasma concentration of the substrate at which saturation occurs. So you got two different things on this graph here. On the x-axis is the transport rate, but on the y-axis it shows you how much of that substrate is in the blood. Let's write that down. Differentiate between saturation and renal threshold. The plasma concentration. At which saturation occurs. So you have to pay attention to the units. For saturation, you're moving some amount per unit time. So they have here mgs per minute. It's a rate. A transport rate in some mgs per minute per unit time. But then the plasma concentration which that occurs, the units are different. It's a concentration. So mgs per unit volume, mgs per mil. It's a concentration, so the appropriate units, mg per mil. So if you're reading this data correctly, saturation is 4. 4 mg per minute happens to be also the renal threshold, 4 mg per mil. Now there's other things we can look at because there are different parts of the nephron. This pretty much refers to these transport maximums to the PCT. Let's use glucose as an example. And we have different things here. We have filtration, reabsorption, and then excretion, which occurs at the collecting duct. So these are different parts of the nephron. Glomerulus, PCT, collecting duct, and you can overlap all the graphs here. So this is what you're supposed to be noticing. I talk about this one. This is filtration, because that's how it gets into the nephron first. And what we learn about filtration is, if the molecule is small enough to make it through the filter, there is no maximum. If it makes it through, and it doesn't matter how much there is, as would be the case in glucose. So, let's see here. What? I already erased it. You can go back to YouTube. Everything's posted on YouTube. Yeah, whatever you think you missed, just ask me, I'll tell you what it is. So the first thing to note, filtration has no max limit. Filtration has no max limit. Do you see that in the data? Here's the concentration of glucose in your blood. The normal range is something like, well, they give you the approximate normal range here. Okay? You can go well past the normal range, and it's all filtered. This never levels off, which tells us it never maxes out. Okay? But you can max this out. So let's kind of make sense of that. Here's a glomerulus. Afferent arterial going in, efferent arterial going out, and then you have around it the Bowman's capsule, and I'll draw a simplified nephron. There's a blood vessel next to it that will help reabsorb whatever's passing through. So let's say you have glucose. Let me just draw a few green balls to represent glucose. And let's start at 100. Let's pretend you filter 100. Okay? And you filter all of it. It enters the bloodstream. And it's all filtered, and it gets through the membrane there, the filtration membrane. It's going to flow past the PCT, and there's some transporter there that will transport it at some rate so that all the glucose is reabsorbed 100%. Because, look at the reabsorption graph, you're functioning submax. So therefore, how much of that glucose is excreted? Say right there. The answer is 0. And do you see that on the graph? Given this is our units of 100. Mgs per deciliter. Well, you look where 100 is, and I don't see any excretion. Okay, so that's basically what we're doing here. So see if you can follow me. I'll just keep going and see if you pick it up. You haven't picked it up already. Let's do 200. Let's double it. So okay, I'll draw more green balls to symbolize glucose, and they all go in there, and they all get filtered, and they all pass by the PCT, and they're all still getting reabsorbed, and you still have no excretion. Let's go to 300. Okay, 300. I'll draw more green balls, and I'll draw them being filtered, and I'll draw them here, and they're all still being reabsorbed, and there's still zero excretion. However, at 300, that's our max limit. 300 mg per deciliter represents what? What's the term? Renal threshold, yeah. You're standing at the threshold, because past that concentration, you will begin to excrete. So 300 is our renal threshold. That little orange dot at 300, it's saturated, okay? Saturation occurs at a rate of 375 mg per minute, right? That's what it says there. So saturation is 375 mg per minute. That occurs when the concentration is 300. So if you go one more, I don't know, go 400. I'll just draw more green balls and more being filtered. You know, this time you're maxed out. So this time you'll begin to excrete. Excretion will be non-zero. So that's why they show at threshold, after 300 is when you start to excrete urine, when you start to excrete glucose in the urine. And that's why all three graphs are superimposed on the last graph here. So filtration overlaps reabsorption to a point. That point is when it reaches saturation, then it just keeps going out. But when you exceed saturation, that's the same point at which you are at threshold. Yeah?
On the charts it says milliliters, but on the board it says deciliters.
It says 100 ml, which is the same thing as a deciliter.
Oh, okay.
Yeah. Oh, okay, so when the blood plasma concentration of a substance, like we use glucose as an example, is so high, when it is filtered by the glomerulus, all of it cannot be reabsorbed because you've exceeded saturation. The amount, quote unquote, left over or not reabsorbed is then excreted in the urine. If glucose is excreted, urine is, quote unquote, sweet, the high blood plasma concentration at which a filtered substance begins to spill into the urine is the renal threshold. So typical questions I could ask, what's threshold? 300 mg per deciliter. That's the answer. Where do you see it on the graphs? Well, this one, you can see it right there. It says renal threshold. Or you could look here. You know what renal threshold is when you max out. You can derive it from there too. Can you derive renal threshold from this data? No. It never maxes out. You can't tell from that. What is T subscript M? Yeah, this is saturation. It's right there. Okay, so know how to read these graphs. What is being, quote unquote, used up in saturation? Well, I'm going for this one here. remember, what's transporting the glucose? Some kind of transporter. And saturation is a transport rate. It's the little molecule transporting the glucose that gets maxed out. You use them all up, and they're all working at their maximum rate. Okay? So when you're saturated, a common mistake is students put glucose. You're not using up glucose. There's too much of it to transport. What's maxing out is the glucose transporter. All right, shifting gears, different topic of the PCT. It can also help acid-base balance. That's a big topic in today's lecture. We'll get to it at the end of today's lecture as well. So you've been looking at these figures a little bit, where you have a cell with a blood vessel on one side, maybe it's the PT or the vasa recta, and on the other side, colored in yellow, is the filtrate. Now I want you to know how these cells can affect pH. Kidney acid-base balance. I say a few things on the board there. Number one, are you reabsorbing bicarb? Our base. Bicarb is our base in this lecture. Number two, are you excreting protons or hydrogen ions? Are you doing both 1 and 2 at the same time? So let me just leave it at those two things. If you put more base in the blood at the same time excrete a proton, what you're basically counteracting is, well, let me say what this does. If you add base to the blood and excrete a proton, you're going to increase the pH, make it more alkaline. Let's look at the picture. If somehow you secrete a hydrogen ion in the filtrate and you get it out of the body in the urine, at the same time you put a bicarb in the blood, if you couple those things, you very effectively increase the pH. But why would you want to do that? That's very effective at counteracting acidosis. Or I guess another word is you're compensating for it if there's acidosis. Counteracts, compensates for acidosis if pH is too low. So let's kind of talk about this. How does the kidney do this? There's some buffer systems, and bicarb's one of them. It's the most filtered base. Okay, I just put a number to it there. You don't have to know that number, but yeah, I mean, you can see it 100% there, and you excrete very little. Okay, so you reabsorb most of it to put base back into the blood. And here's one buffer system you need to know: the ammonia buffer system. Because what you need to know is, you can't, I wrote this on the board, but this is untrue. You cannot excrete a hydrogen ion. It's too small. It'll just attack a tissue. So you have to kind of glob it onto a larger molecule, a buffer, and then you can excrete that. And one of those buffers is ammonia. So notice where we are in the nephron. There's different parts of the nephron that can function in acid-base balance. This happens to be the PCT, okay? So this depends on, remember, proteins are made of amino acids. Amino acids have ammonia groups. One of the amino acids is the amino acid glutamine depends on this system. When you metabolize glutamine, you deaminate, oxidify, acidify, metabolize. Let me just draw the amine group. We call it ammonia, NH3. When you acidify it, you basically stick on a hydrogen ion, a proton. Okay? And when you do that, think of that as NH4 plus. It's basically an ammonium ion. So ammonia, when you acidify it, is basically an ammonium ion. That's where the proton goes. You can excrete that. And so you need to look at the figure to see that. The ammonium ion is excreted out in the urine, and that's coupled with the reabsorption of bicarb. Now, it may be hard to read there. That says new, because they call it new for a reason. If you add a base to the blood at the same time excreting an acid, that makes the base win. It's like one notch above. Get rid of one, add one, that makes the base new. If you added a base at the same time as adding an acid, they just kind of neutralize each other. It ain't new. You have to couple them to make it new. So, excrete the ammonium ion at the same time, reabsorb bicarb. This will effectively compensate for acidosis. You got to couple it, is the thing. Okay, another buffer system. This is not in the PCT. This says type A intercalated cell of collecting duct. So this is a cell found in the collecting duct part of the nephron. It can do this. Well, it's the phosphate buffer system. Let's write that down. Phosphate buffer. From this chemistry equation, when you hydrate CO2, you get a carbonic acid, H2CO3, and that's a weak acid. It dissociates into bicarbonate and a hydrogen ion. And that's shown happening inside the cell. There's carbonic anhydrase in these type A intercalated cells. California, or carbonic anhydrase, basically is in type A cell in the collecting duct. Okay, so here are our products right there and right there. And the question is, what does the cell do with the hydrogen ion? It excretes it and combines it with monohydrogen phosphate, this molecule. Monohydrogen phosphate. So when you glob a proton onto that, you get H2 dihydrogen phosphate. And that's the molecule that's excreted. And you couple that with the reabsorption of the bicarb. Once again, you get rid of the acid, you get a new base that helps counteract acidosis. Like the third one your book talks about is the bicarb buffer system. That again happens in the PCT cell. Bicarbonate buffer system. Okay, this one, it makes sense to me to look at their last step first. Look at number 6. They show you a CO2 molecule diffusing into the cell. CO2 is a small inert gas molecule. It doesn't need a transporter or anything like that. It just diffuses into the cell. It starts there. Okay. CO2 diffuses into cell, and what you got is the same equation as before. I'll write it again just to be clear. Okay, now what does the cell do? Well, this time it's going to take the hydrogen ion and it's going to excrete it. Okay? Now, look over here. Here's the hydrogen ion. And look at this. Just tell me, where does it disappear to? Where is it hiding? Where does it go to? Ultimately, it ends up down here somewhere. Is it, I know I'm being kind of rhetorical. Is the H in the CO2? No, there's no H. It's in the water. Okay. Now that's kind of funky that you have it in water, because water is hiding the proton. Think of water as a hidden proton. You're taking this, H plus OH. That's water. That's H2O. Now, what have we been saying about reabsorption? You reabsorb most of water. So are you getting rid of the proton, the hydrogen ion? No, you're not. Water, mostly reabsorbed. So in terms of just getting rid of the hydrogen ions, you're not doing it. Okay. But you are reabsorbing, if you look at the figure. All right, reabsorb, bicarb. So number 1, circle it, reabsorb bicarb. That's good, you're replenishing your base, but you're also reabsorbing the proton hidden in water. So this buffer system, while it replenishes your base, it does not help to combat the acidosis as well, as good. I don't know, as well as good, but because you're reabsorbing the water. Let's see here. Okay. Oh, there's another point I wanted to make. The question that's always asked by me in the book is, they say that bicarbonate is indirectly reabsorbed. Let me write that on the board. Bicarbonate is indirectly reabsorbed. It's not a direct reabsorption, it's indirect. Let me explain that by saying, if you directly reabsorb bicarbonate, you take the bicarbonate here that's in the filtrate and you take that molecule and you suck it, transport it all the way over here directly. That would be direct. This is not direct. You do reabsorb bicarb, however you do it indirectly. Here's the thing that enters the cell, CO2. Okay, and then you put it through this chemistry equation, that bicarbonate is reabsorbed. All right, so that's what is meant by indirect reabsorption. The other thing to notice is they don't put new next to the bicarb that's reabsorbed there. That's on purpose. Why is there no new here? Is it new? It isn't, because you didn't get rid of the proton. And it's hiding in the water. Yeah, so that's another point. Those are like little details that may escape you if you're not thinking carefully. All right, so I answered this first question. It's indirectly reabsorbed. And students tend to, all right, how does glutamine metabolism increase pH? What buffer system was that? The ammonia buffer system. Yeah. Students tend to forget the word glutamine on the exam, so try to put a star next to that. Make sure you remember that amino acid.
Professor, did you say that the tricarbonate buffer system is the least effective?
Yeah, because you're not coupling the excretion of the proton with the reabsorption of the base. You're only doing one of them, not both. Not as effective. All right, so I'm going to shift gears from acid-base balance. We talked about PCT and renal corpuscle already. The next part of the nephron that needs more details to be explained is the loop of Henle, also called nephron loop. Kidney can help regulate blood osmolarity at 300 milliosmolarity. You do it by pulling water and salt out of the filtrate. Okay? So the loop of Henle, what it does, its role in this, it uses a countercurrent mechanism to pull lots of water and salt from the filtrate. This dramatically varies urine concentration. In doing so, you can maintain blood osmolarity at 300. So I guess 300 is kind of the number in the middle. Milliosmolarity. That's pretty much like saline, which is like saline. .9% NaCl, that's saline. So it's pretty dilute. Okay, 300 is a high number. It sounds very concentrated. It's not. It's basically the saltiness of your plasma, which is like similar to the saline. So imagine you have a little graduated cylinder, fill it up to 100 ml, and just add 0.9 grams of salt. That's not very much. Okay, but that's what that 300 basically is. It's pretty dilute. Now, and this is what is entering the loop of Henle. Now, the ones we're talking about are of the juxtamedullary nephrons. This one, not this one. Okay, so we're talking about the countercurrent mechanism of this one, how that can help concentrate urine. So here's a figure, another figure from the book. It says right here, the long nephron loops of the juxtamedullary nephrons create the gradient. They act as countercurrent multipliers. That's what we're talking about here. So this thing is a multiplier. What does it create? This salt gradient. Here we have cortex. If that's cortex, what's this dark part? Medulla. Okay, it's a renal pyramid. And notice the saltiness of the cortex is that kind of saline neutral 300. But notice if you get progressively deep, it gets to like 1200. Here's the whole pyramid. Maybe it's 300 here, but then it gets progressively more salty. By the time you get down to here, it's like 1200. So you multiply the saltiness from top to bottom. So you want the medullary interstitium to have a salt gradient. Medullary interstitium has a salt gradient from 300 to 1200 milliosmolarity. And on a somewhat superficial level, we want students to know how the long loops of the juxtamedullary nephrons create that 300 to 1200 gradient. Juxtamedullary nephron loops create this salt gradient. Using a counter current multiplier. It's basically a positive feedback loop, which I'll describe in a minute. And so, two things to know. What is meant by the countercurrent multiplier for the loop, but also talk about the blood supply. Because if you're trying to establish a salt gradient, well, the tissue still needs blood, but you can't have the blood flow through and wash it away. So you need the blood supply, which in this case is the vasa recta, to act as a countercurrent exchanger to preserve the salt gradient. So I'll explain both. Let's do this one first. The loop of Henle, what is meant by countercurrent multiplier? So this figure can help. It's the easiest way to explain it. Since it's a loop, it's a U-turn, hairpin loop, and this is where we begin. Filtrate comes down, takes a U-turn, and goes back up. And here's what's happening along the way. On the way down, call this see how there's like descending, but it's like thick, and then it gets kind of thin? Let's talk about the descending thin limb of the loop of Henle. So LOH a countercurrent multiplier. Think about it in two segments, on the way down and on the way up. On the way down, let's consider descending thin limb, or thin descending limb. What you need to know about that limb, it's water permeable. Water can escape. Well, or enter. Now think about it. You're putting a filtrate in. The filtrate's coming in at 300. It's dilute. And notice how they color the filtrate. It gets darker and darker and darker, implying what in terms of concentration? It's getting more concentrated. Why? It's losing water. Why would it be losing water? What are the rules of osmosis? Look at the interstitium. It's getting more salty. So if this is 300, water is going to go towards more salty. So on the way down, the filtrate loses water. That's basically what you need to know. The thin descending limb is water permeable. Water leaves, filtrate, concentrating it. You get to the bottom. I call it the elbow. Assume the filtrate has equilibrated with its environment, the interstitium. Just give me a number. What's it going to be? 1200. Yeah. Filtrate concentration at the elbow is 1200. That's the filtrate. It's simply equilibrated with the interstitium. Okay, now it's countercurrent, so it's going to go down, then it's going to go up. So what's going to happen there? So notice the ascending portion, there's a thin part and a thick part. Thin part and a thick part. Let's mostly just talk about, I call it the TAL, the thick ascending limb. TAL for short. Basically what you have there are two things. One, this one's watertight. It's impermeable to water. There's tight junctions in there. That's one thing to know. So water cannot escape on the way up. Water, impermeable. Also, there are these salt pumps that were not in the descending limb. It's got salt pumps. NaCl pump. It's going to pump it out, okay? So on the way up, you don't lose water and you pump out salt. And there's plenty of salt to pump out because you kind of concentrated the filtrate on the way down. So as it goes up, you pump out all that salt. So think about that. No water leaves and you pump out salt. No water leaves, and pump out NaCl. What do you do to the filtrate? Do you concentrate it or dilute it when you do this? It becomes more dilute. You're not losing the water and you've drawn out the salt. And they show that. They draw it from like more brown to less brown. Dilutes filtrate. Effectively dilutes. So let's put it all together. This is what I want you to know for both limbs. How does that, what effect does that have? So let me put it together for you here. Now this is a positive feedback loop. This isn't my figure, it's from the publisher. I like it, except for one thing. I never like where they start in the cycle. Good thing it's a cycle. I can start wherever I want. I'll end up here. Let's start here, because this is where I started teaching it, in the thin descending limb where the filtrate enters. Let's start there and go through the process, and all the time think to yourself, how is this a positive feedback loop multiplying the gradient? Let's go through it. So when you come in the thin descending limb, I'll call it TDL for short, you're coming in and water leaves descending limb. Okay, we said that. Water leaves. Put a circle around that. the next point that we said was, well, that increases the osmolarity, right? Increase OSM. In fact, we even said that at the elbow, it maxes out at like 1200, right? It's 1200 at the elbow. So we've concentrated the filtrate. We've made it very salty. Then they say, so you're increasing the osmolarity of the filtrate entering the TAL, okay? So that 1200 milliosmolarity, a very concentrated filtrate, enters TAL. Salt pumped out. TAL pumps out salt. Said that. Then the top part is the key. Oh, well, that increases the interstitial fluid osmolarity. I'll just say it another way, increased saltiness of the, the interstitium. Put a thing around that. So, if you've made the interstitium more salty because you've pumped it out, well then isn't more water going to leave on the way down? Yeah, it is. And then it's going to be more salty, and this keeps going around and round. Because the flow of the filtrate is side by side, it affects each other, okay? As long as you keep pumping salt out, and you increase the saltiness in the medium, on the way down, more will leave. Okay, you're gonna get more salty in the elbow, and that enters, you pump it out, you keep just going around and around and around and around. Okay, the end result is net effect. You've multiplied the medullary interstitium from 300 to 1200. You've multiplied medullary interstitium from 300 to 1200. That's units of milliosmolarity. It's actually way more complicated than that, but I can't even understand it past this level, so that's all you gotta know. And this is all your book presents. I think it's good enough. Next question. Okay, so you've established this wonderful salt gradient. This is great. You need part of the kidney to be salty, because that way, dilute filtrate coming through, you'll pull the water out. All right? Remember, we're trying to concentrate urine so we don't lose all of our fluids to the urine. We want to keep it in the body. Kidneys are great at pulling our fluids out of the filtrate, so we keep it. So that's why this salt gradient is very important. So the next question becomes, how do we keep the blood supply from washing out this salt gradient that we've established by the countercurrent multiplier? So the vasorecta act as a countercurrent exchanger. vasorecta acts as a counter current exchanger, thus preserving the salt gradient. Thus preserving salt gradient. When I say salt gradient, I mean the 300 to 1200 thing. You don't want to mess with that. Just leave it alone. So it does this by making passive exchanges with the interstitial. Makes passive exchanges of water and salt with the interstitial. Now, a question for you, aside from that, does this figure show gas exchange at the vasorecta, yes or no? Does it show gas exchange? Yes. Blood coming in, oxygen rich, it's red. Blood leaving, blue. Gas exchange does occur, right? So that's happening because we were just trying to supply blood to this area, just like anything else. The twist is, how do you supply blood without washing away the salt? Because as blood comes in, blood is going to be 300 because it's like, you know, the concentration of saline. Comes in 300, but if you're putting dilute blood through a salty medium, this capillary bed will just exchange water and salt. So the rules of osmosis say water will leave the blood and salt will enter, right? Try to balance each other out. So get down here, you equilibrate with the environment, 1200. Okay, here's the kicker. You see how this blood vessel is U-shaped? You usually don't see that. Usually just blood flows, blood is a blood stream, and it flows right through. Blood is usually not a U-turn. Okay, that's what's different. Because if it were the usual blood just flowing by, it would be 1200, and then it would just keep on going. And it will remove all the salt that it took up. But that is not the case. It is a U-turn. So you get here, it's 1200. What happens on the way up? Now this concentrated blood is getting less salty. So again, it makes passive exchanges. So while on the way down, it did this. I'll just say quote unquote on the way down. Because on the figure I'm looking at, it's going down. You lose water, gain salt. So blood becomes concentrated, 1200 milliosmolarity. But then, on the way up, you continue to make passive exchanges. As you go up, the environment becomes progressively less salty. So you've concentrated the blood. Now you'll gain water, lose salt. Just rules of diffusion and osmosis. On the way up, lose salt, gain water. Therefore, you're going to dilute the blood. Look at the concentration of the blood as it leaves. It's about 300, 325. So we saved a lot of salt. We didn't remove it all. Okay. So the net effect of this is you do not remove salt. You don't mess with the gradient. You just kind of left it intact. Don't remove salt just, well, you accomplish this. You protect gradient. So I've asked you a question like, be very careful about the words that I say on a test question. Does this countercurrent exchanger, does it create the gradient? Yes or no? Does it create it? The answer is no, it doesn't create it. What created it? That was the other thing. We can say, this creates it, okay? This just protects it, it just leaves it alone. It doesn't wash away the salt gradient. Okay. All right, so any questions on that? Whether that's lubothenling, we've talked about how it concentrates urine, multiplies, exchanges. That's a good one. Remember from my job interview, they wanted me to teach this. Like, oh, great. It's one of the more difficult things, but it's not so bad. All right, the DCT. It gets easier now. You know why? Because we've done most everything. We've talked about filtration. We've talked about the PCT. They did most of the work. By the time the filtrate gets here, most stuff is gone. The only thing that's left is a little bit of water and salt. And the question is, do you want it? So I'm writing water, salt. Reabsorption? Question? Because you may want to do it or not, depending on if you're dehydrated or not. Okay? Depending on if blood pressure is low or high. And I'm not going to say too much about it because it's ground already covered. Remember studying that on the first test? We talked about aldosterone and we talked about how it's secreted from the adrenal cortex. Zona glomerulosa. Well, remember that. Is it coming back? Zona glomerulosa, here it is. It's a steroid, and it binds its receptor in the cytoplasm, and it increases salt reabsorption. And water doesn't follow unless ADH is present. I kind of emphasized that earlier, but that's basically all you need to know. The hormone aldosterone acts on DCT cells. If you look here, it says lumen of distal tubule. So that's where we are. Lumen. Aldosterone acts on the DCT and facilitates sodium reabsorption. Then water follows if ADH is present. So after the DCT are the collecting ducts. Maybe you reabsorb water and salt or not at the DCT, and you get to the collecting duct. And now this is your last chance to modify the filtrate. And you can either form dilute urine, which is kind of like the color of straw, or this darker colored concentrated urine. All right. And how the kidney does it molecularly, the formation of dilute or concentrated urine, is ADH present or not. In the presence of ADH, 99%, excuse me, it's 99% of water is reabsorbed. So I guess these ADH and aldosterone slides are kind of like the bookends of my course. They're on your first test, they're going to be on your last test. This one here is showing you the action of vasopressin or ADH. Collecting ducts, the formation of dilute or concentrated urine. It really depends on the presence or absence of ADH, because if ADH is there or not depends upon the presence or absence of the aquaporins that we talked about before. Well, let me not gloss over this too much, but what you should remember about ADH, it's an antidiuretic hormone. A diuretic increases the urine output. An antidiuretic will decrease it. So, filtrates here, it's watery, and you're dehydrated. So this hormone binds its receptor on the cell surface. It sends a second messenger to mobilize these vesicles to fuse, and that their water pores, aquaporin, will insert on the luminal side. Therefore, water will follow by osmosis into the bloodstream. That's the reabsorption of water. So that's what you had to remember about that hormone from the first test. So I basically tabled it out here. On the left side, if you're overhydrated, no ADH, decreased aquaporins, dilute urine. Overhydrated versus dehydrated. Overhydrated, the salt in your blood is diluted. There's osmoreceptors in your brain. It's not going to secrete ADH. No ADH. No aquaporins. And so the filtrate entering the collecting duct is 100 to 300. Here they show it to be at about 100. Okay, it's very dilute. Maybe and that enters, and it goes through the collecting duct. You put it through the salty interstitium. There's tight junctions between the cells. Water cannot escape the collecting duct. So it just enters 100 and it leaves 100. So urine output is increased. Increased urine output, and you're going to form dilute urine. To put numbers to it, it varies. Pretend each of these cups symbolizes a liter, about 6 liters per day. It's a lot. And the concentration of it is about 100 milliosmol. Milliosmolarity. Okay, there you go. So, you're dehydrated. The opposite. This is the other end of the spectrum. You have lots of ADH. You max out the aquaporins. The urine output decreases. You're reabsorbing all the water. You don't want to lose any of it to the urine because you're dehydrated. So maybe you're down to about a half liter a day. You decrease urine output. It's very concentrated. Concentrated urine of about 1,200. So on the figure, water is allowed to leave the collecting duct. It's just going to follow its osmotic gradient if the aquaporins are there. Okay. And urea helps. I haven't mentioned urea yet, but that's this slide here. It's called urea recycling. It's actually a metabolic waste product that you use. Recycle it. So urea is a metabolic waste product, but the nephrons recycle urea to help reinforce the medullary gradient. It enters the thin descending limb. In the cortical collecting duct, urea stays in the nephron as this area is dilute. But deep in the medullary region, now highly concentrated, urea leaves, forming a pool of urea that recycles back to the thin descending limb. ADH increases urea. So the recycling is simply this. It's here. It goes up to the thick ascending limb. It goes to the collecting duct. It stays in the filtrate because it's dilute here. But when it goes down the collecting duct in the presence of ADH, it gets super concentrated, it leaves. Okay, and it just kind of goes up and it just keeps going around and around and it keeps leaving, and it helps, the urea helps concentrate this part of the interstitium. So it's called urea recycling. ADH helps this. ADH reinforces urea recycling. This urea recycling, it's helping to, that reinforces the medullary interstitium. That in turn helps reinforce this salt gradient I keep talking about.
Professor, I have a question.
Sure.
So we know all this to be true, but what happens, you know how they say if you have diabetes, you get really thirsty and your urine output is, you pee a lot.
Yeah. Well, that's because the high glucose in the blood gives you that thirst. Okay. I don't know if that has to do with this, but you urinate a lot because the thirst makes you drink more. And then it also, in the kidney, if there's a lot of glucose, it'll pull a lot of fluids into the filtrate because the glucose is in the filtrate and it's normally not there. That's another reason why you have to increase urine output with diabetes. Yeah. So think about that. Glucose in the filtrate is normally not there. That increases the osmolarity concentration of the filtrate. Water wants to enter the filtrate because the glucose that's there to help dilute it. Increases the urine output. Yeah.
All right, thank you.
Mm-hmm. I always feel really thirsty after I eat pizza. I know exactly why. It's very salty. That makes you thirsty. Okay, collecting duct. Let's get back to that. So we're talking about the collecting duct more. So we're talking about collecting duct over there because of the aquaporin thing. Now I want to talk about it in terms of its ability to do acid-base balance. And we already talked about it halfway. I mentioned these cells, but now I want to talk about these cells. Talked about the A cells, now I want to talk about the B cells. So in the collecting duct, there's basically what they call the principal cell and these intercalated cells. You can find those. Collecting duct, principal cell. They call it principal cell simply because it's mostly that cell type that's in this collecting duct. It's the principal cell. This is the cell that does this. It's got the aquaporins. It functions in water and sodium balance. That's what it says on the slide there, right? I'll just say it responds to ADH to help you get concentrated or dilute urine. The other cell that's kind of few and far between are the intercalated cells. And there's two types. There's type A and type B, know them both, but both of these, the A or the B, they function in acid-base balance. So here they are. Let's just kind of look at them. There's this. Here's the A cell. Filtrate blood on this side. Here's the B cell. Filtrate blood. So what's happening in terms of acid-base balance? The A cells, we said this before, they use the phosphate buffers. You excrete the hydrogen ion, you reabsorb the bicarb. That's what they're showing here. Excrete the hydrogen proton using the phosphate buffers, reabsorb bicarb. This would effectively, when you think about it for a second, how's it going to affect pH of the blood? It's going to raise it. What we said earlier is that compensates for acidosis. Acidosis, pH getting too low. These work, that can help bring it back up. Okay, the filtrate, you're just rearranging the furniture. You're just putting the base pump, instead of on basolateral, put it on the luminal side. And for the acid pump, just get it out of the luminal side and put it on the basolateral side, just flip-flop it. So you do the reverse. The B cell will excrete base, reabsorb the hydrogen ion. That will acidify the blood. That will drop the pH. That's effective against compensating against alkalosis. The pH is getting too high. So if I just kind of show you information like this, could you tell which cell type this is? A or B? Excrete, base, reabsorb the acid.
So decrease in
Yeah, so which cell type is it? Yeah, the B is the one where you excrete the base and reabsorb the acid. So on this question, the correct answer is B. All right, let's take a break, and we'll finish these slides when we come back, and then we'll have plenty of time for a dissection lab. Come back in 20 minutes.